We are often unaware of the true causes of certain observed phenomena in the world around us. We sometimes do not even guess about the relationship between the observed phenomena, which seem to us to be independent of each other. We can offer different explanations for such phenomenon, but today we will talk about the situation in which the speed of the physical process itself exceeds the speed of data about it. At the end of the previous video titled Physics as an Information System, it was suggested to consider a mental experiment in which the speed of a physical process noticeably exceeded the speed of data transmission about that process. I promised that I would continue this topic in the current video. I will briefly repeat the description of this mental experiment. Let there be a stationary observer who has a sonic direction finder and a clock. In a cloudy sky, excluding visual observation, a supersonic airplane makes a straight and uniform flight. The observer is unaware of this. He does not know what is flying, at what speed it is flying, or at what altitude it is flying. Moreover, he knows nothing at all about what is happening in the sky. His task is to make a picture of the sound observation of the airspace. Let's try to reproduce the observation pattern. At some point in time, our observer will note the appearance of a point source of sound in the sky. And then there will be an observable splitting of this sound source into two, which will fly away in directly opposite directions. Since we, unlike our observer, know all the initial conditions of the mental experiment, we can easily explain why he observes such a situation. The moment of appearance of the point source is the moment when the sound of the flying airplane first reached the observer. The bifurcation into two sources is explained by the fact that the sound of the previous moment and the sound of the subsequent moment of the supersonic airplane flight began to reach the observer. This can be clearly seen in the figure. What conclusions can an observer come to based on the picture of events recorded by him in a cloudy sky? Analyzing bearing taken at equal intervals of time, our observer is likely to come to the following conclusions. First, the source of the sound appeared suddenly, as if from nothing. The fact of its appearance cannot be explained by its falling from the upper atmosphere. In such a case, the source would have been stationary for some time and would have remained point-like. But it began to bifurcate from the very first moment of its appearance. Second, there was a division of the original source of sound into two, which began to fly apart with different speeds and with negative acceleration, that is to say, with braking. As can be seen, the model of what is happening, built on the results of observations, is completely different from reality. By the way, the picture imagined by the observer is conceptually very similar to the Big Bang theory. Indeed, the point of origin of sound can be taken as the singularity point. And the dispersion of two emerging sound sources with a slowing down of speed can be interpreted as an analog of redshift. So why did the observer get this result and come to the wrong conclusions? Obviously because the speed of the airplane flight was higher than the speed of sound. In other words, remembering physics as an information system, the speed of the physical process was higher than the speed of data arrival through the information channel. That is why, processing the received data, the observer made his wrong conclusions. After all, when observing physical processes running at a speed higher than the speed of data arrival about this process, one may not guess about it. We see this situation from the outside and realize the observer's error. Let's try to understand whether the observer within this mental experiment is able to understand what is happening in the sky. He can think of dozens of variants of occurrence of objects in the sky and even calculate their trajectory. But he will always come to the conclusion about two objects, unless he considers the variant of motion with supersonic speed. Suppose an observer remembers that objects in the sky can move faster than the speed of sound and decides to analyze such a variant. In this case, he will correctly describe what is happening in the sky. But for him all variants will be equal, both for two objects flying with speeds below the speed of sound and for one object moving with exceeding the speed of sound. Our conditional observer will not be able to find the only correct answer, because he does not have additional data about what is happening. But, for example, if our observer had the ability to record the change in tone of sound signals, he would be able to correctly describe what is happening in the sky. Yes, we're talking about the Doppler effect. Although for sound waves it is incorrect to reason about color shifts, but for figurative representation, let's say so, the conditional blue shift of the sound frequency will show from what direction the airplane is flying. In other words, the object is flying from the side in which the tonality of the sound signal increases. Anticipating the release of the video in which I skeptically consider the topic of relic radiation, I want to dwell on one fact, which well illustrates the conclusions drawn in a mental experiment with the flight of supersonic aircraft. This is a map of dipole anisotropy or dipole irregularity of the background radiation of the universe, compiled from data from the Orbital Observatory WMAP. The red horizontal stripe is the light from the Milky Way galaxy, at the edge of which our solar system is located. In this map, the colors show the intensity of the deviations of the background radiation, but this does not affect the pronounced dipole anisotropy. Let's try to look at this map by analogizing the correct conclusions from our mental experiment. Why not assume that the presence of red and blue shifts is caused by a process occurring at superluminal speed? I'll also note that observing a process whose rate exceeds the rate of data about that process always comes with some constraints. In the limit, this is the observability boundary, which I will talk about in one of the next videos. So subscribe to the channel so that you do not miss the most interesting things. Now let's look at the picture. What does it show? The expected answer is that it is a sequence of pulses. And to the question, what generated this sequence of pulses? As in the case with the observer's interpretation of supersonic airplane flight data, there may be several answers. And all of them will be equally true for the person looking at this picture. Let's try to answer that question. 3 ideas came to mind right away. The first one, this is an ordinary sinusoid, limited in level, for example, with the help of diodes, which formed a kind of band-pass amplitude filter. Second, such a sequence of pulses can also be obtained as a result of the inverse Fourier transform, during which a pulse sequence is obtained from a set of sinusoids with different frequencies at the output. Third, another obvious way to obtain such a sequence is to apply a key electronic circuit, such as a simple multivibrator. The example with a pulse sequence can be considered as a simplified analogy of observations of a process, the reasons for the appearance of which we do not really know. And if we do not know the causes, we cannot accurately predict the further development of the process, especially when it comes to near light speeds or the microcosm. I like one more analogy based on frequency modulation. For non-specialists, I will explain this as one of the options for modulating a carrier with a useful signal during transmission, say, using radio waves. Suppose we have some carrier as a process running at a speed greater than the speed of light. There is also some modulating process whose speed can be both less and more than the speed of light. Such modulation will generate a mass of harmonics, some of which may well be below the speed of light and thus become available for human observation. The appearance of such harmonics may be pulsed. And this is where the most interesting part begins. But first, let us recall an important debate among physicists over several hundred years. This is the debate about the nature of light, which goes by the name of the corpuscular wave dualism of light and from which the present quantum physics was born. While at the beginning of the 19th century, after Thomas Young's experiments with the passage of light through narrow parallel slits, no one questioned the wave nature of light, At the beginning of the 20th century, a sufficient amount of experimental data had accumulated that could not be explained at that time by the wave theory. Therefore, Isaac Newton's hypothesis of corpuscles, light particles, which are now called photons, had to be recalled again. In order to somehow reconcile the two approaches, which are indeed observable, physicists became clever theoretical constructs. Or maybe it's much simpler than that. Let's consider light not as an independent entity, but as an information flow with data about physical processes unknown to us, running at speeds above the boundary of observability, that is, above the speed of light. And now let's go back a little bit and represent harmonics at modulation of the superluminal process as photons. Thus, the connection between the corpuscular and wave properties of light becomes clear. In terms of the previous video about physics as an information system, light can be considered as data generated by a process with a superluminal speed. Then it is easy to explain some observations in quantum physics, for example, interdependence of quanta, which has received the name of quantum entanglement. In short, there are quantum phenomena, but there are no quanta. If you are not convinced by my reasoning, I recommend you to look at the stroboscopic effect as an analogy of observing a process at superluminal speed. In the next video I will consider the question what is the boundary of observability and how it affects our perception of the world around us.